Are we live? Hello? Hello world? Hello world? Give me just one moment. Pause this here. Get the chat over here. Say howdy doody everybody. Welcome. Hello, hello. And get this chat over here. And there we go. So, hello everyone. We're going to look today at this question. It's an interesting one. Count complete by tree nodes. Yeah, we'll look at this one completely. There's another question, there's a couple other questions I was thinking about too that I wanted to kind of make comments on, but we'll leave those for now. Excuse me. So, yeah, count complete by tree nodes. So, this is an interesting question. And by the way, this one is kind of a little more near and dear to my heart than others. Reason being, I actually got this question in one of my interviews at one of the FANG companies, one of the top companies. I actually got this question, and I tried to do this sort of on the spot. I had never seen this before. This is my first time seeing it. This was the first. That was the first time seeing it. So pretty interesting question here. So I kind of already know the answer, but we'll go through it. So given a complete binary tree, count the number of nodes. Note, definition for complete binary tree from Wikipedia. Given in a complete binary tree, every level except possibly the last is completely filled and all nodes in the last level are as far left as possible. It can have between 1 and 2 raised to the h nodes inclusive at the last level h. So it's a completely filled binary tree except the very last level. It could have any number of nodes, but they're all going to be pushed as far to the left as possible. They're all going to be, nodes are as far left as possible, right? Which is interesting. So you might think immediately like, oh, well, if it's filled, then you just find the depth, and then the depth you take 2 raised to the, I think it's, how does it work? It's a sum of it's a geometric series, right? 2 to the 0 plus 2 to the first, etc. And geometric series have a clear pattern. What do you call it? Geometric series have a closed form summation. The geometric series have a closed form formula for the sum, and which actually if it's and for geometric series of 2s, a binary geometric series, I guess, or I guess where the ratio term is 2 is exactly 2. It's actually really, it simplifies to I think, so here would be if the depth is h or the height is h, then so it goes 0, 1, 2, 3. The height would be, I guess if the height is, it depends on how you define the height. Like if you had to say the height is 0 of a tree that has 1 node in it, then you would say it's going to be the height minus, height plus 1, 2 raised to the h plus 1 minus 1. So you just find the depth, basically, and you can quickly find how many nodes are in the tree. And that's logarithmic in the number of nodes in the tree. However, there are a couple things here. One, you have to be careful because the depth is at least 2 things here. One, finding the depth. So the thing to note here that's special is that this extra that would be true if the tree was totally filled. However, the bottom level is not necessarily filled, which leads you with you have actually sort of 2 problems. One is the oh no, actually no. Oh, okay. So it includes 1 node always at the last level. So there's always going to be a node. If you bear down on the left side of the tree all the way down, you'll always find the height. The question then, so actually you can find the depth very quickly, very easily. However, you do have one question of, then really the issue is you have to figure out how many nodes are on the last level, right? And you can actually just decrement that height. So let's see, if we make the height 0, 1, our formula, we said it's going to be 2 raised to the h plus 1 minus 1, which is h is 1, so 2 squared minus 1 is 3, which is correct, right? There are 3 nodes. So yeah, so you would subtract 1 from that height to get the sort of internal nodes, however many that is, and then you'd add that at the end. But now you need to figure out how far to the right do these nodes go. So I couldn't find a really simple, I couldn't find a constant time way to figure that out. Excuse me, my pants are a little uncomfortable. I couldn't find a constant time way to do that in the interview at the time. However, I could imagine like a binary search, a logarithmic approach, kind of divide and conquer approach, where you would say, okay, basically you would say, all right, is this left subtree totally filled, right? Yes or no. If it is, then you're gonna take a look at the right subtree. If it's not, then if the left subtree is totally filled, then you're gonna take a look at the right subtree. If the right subtree is then not filled, that means you actually you found the last node. You found the position of the last node, and in the what do they call that, in the tree, in the complete tree, in the I guess the parent, I guess the total tree, the whole tree. So you could kind of think of a recursive approach doing it that way. Actually, what I ended up doing was I used a binary search where I would use a logarithmic, and you could figure these things out in logarithmic time, right, and time proportional to the height, because all you need to do to figure out if the left subtree is filled is bear down all the way on the right side of it, right, and you can tell immediately. If it's not filled, then you don't need to care about the this right subtree. If it is filled, then you want to check this right subtree. And if this right subtree is empty, completely empty, then you're actually finished on this left side. You found the index. If this right subtree is not empty, then you can forget about this previous subtree. So I would want to write, I guess you can write a recursive routine. Like, I'm thinking there's a better, so the way I had done it previously was I literally bore down to at an index, right? I figured there's a way to bear down into a particular index. So I would try to take like halfway through the bottom here and say, okay, if there's a node there, you want to look to the right and then see, okay, are there any nodes there? And if there is a node there, so I got kind of messed up on this one, right? This was sort of the classic, like, implementing a binary search but doing it kind of poorly problem that I've run into many times, where in theory this works. Like, you bear down in the middle and you say, okay, I see something there, so keep that in mind, and then say, all right, is there anything to the right of it? So take a look at the right side and you say, okay, there's nothing in the middle there, maybe. So then go to the left side between those two, and pretty much once you've determined there's either nothing there or you found something new, then you sort of, I guess what's ultimately going to happen is you're going to end up in a point where you found something and then there's nothing to the right of it. That's kind of what the search is going to do. Now, programming that correctly is challenging. That's kind of what I think I may have failed this question the first time I did it, because I ran into that same problem where it's really kind of wonky, kind of funky to program that search. like neatly and concisely. However, if you use a recursive function, I think you're in much better shape. So what you can do is, and by the way, every call to sort of check an index, particular index, would require, for starters, you have to kind of have like left and right maneuvers to get down to that correct index, and then you also need, so based off of that index, you've got to write a routine to actually get down there to check if it's null or not, and then depending on if things are null or not, then so what I think what I could have done is I could have used the routine. I could use and could have used this routine, and I can do this in the future too. There's a way to write this in general, this binary search, or rather the search routine, where if I assume what I'm looking for ultimately is true and false are the numbers in this array, right? They're either true or false, either the node's there or not. And I'm looking for the first time in this, we'll call it a quote-unquote array, or this part of linear sort of piece of data. And what we're looking for is the first time that we see a value as we're looking for the first time that we see a value that is greater than. And actually these are all true on the left side and false on the right side. So we're going to actually be looking sort of backwards. We're going to be doing, the comparator is going to be sort of backwards. So actually, I could even use this subroutine. I can even use this lower bound subroutine, C++ lower bound subroutine, and write the comparator correctly in such a way where what you're looking for is you're actually going to be comparing indices, and each of those indices are going to run a subroutine which is going to return true or false, and they're going to run a subroutine on each indice, and it's going to return true or false, and we're actually going to do a greater than comparison. You're going to do a greater than comparison, which is to say this returns true when A is greater than or equal to B, I want to say, or yeah, A is greater than B. So I'm trying to think how this works. So if we did, like, let me just try something kind of locally here to get practice with this. So I'm pretty sure I could do this in kind of a nifty way. Like I was thinking I could actually write the lower bound routine, but you don't need to. You could just write a comparator. So this actually is not. I think I could have done this correctly in the interview and concisely to the same idea that I had. But let me just see, like, if you have an array that looks like this. Let's just say standard array of integer or just booleans, and let's make it look something like this. Say test, and it's going to be 1, 2, 3, 4, 5, right? And then now we want to say standard lower bound of, we actually want to do true, true, true. Let's do it this way: true, 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 false, false, right? Standard lower bound, and we're going to use test.begin, test.begin, end, and we want to say comp1, auto comp1 is going to be like this. And we want to say, okay, const reference, I guess booleans, right? A and const boolean B, right? So we're going to return A less than B, And then we want comp2, which is the reverse. And also we can do test 1 and test 2, right? Let's get some practice here. And we want to reverse these for test 2. This gets a little confusing. Okay. Now, this, we're going to reverse this. There's going to be A less than B and A greater than B, right? So there's auto P1. And we want to standard out, cout P1. So the lower bound, I think we're going to find the first value that's greater than or equal to the thing that we're looking for, which is, now we have to give it a value and a comparator, right? So the first thing that's greater than or equal to, we'll say true, right? Something like this. First time that's greater than or equal to true. The thing that's interesting is, I think this should give us the first false, and then we're actually gonna false, right? And then P1 minus 1, or rather, like this. And this should be true. Oops. And I want to see what happens here. What do we get for the printout? Like this is kind of a fun exercise, not a fun exercise. Well, yeah, kind of a fun exercise in finagling with this comparator and this sort of binary search, Boolean search. Stack buffer overflow. Okay, so let's try this. Where does it occur? This overflow. All right. Okay, interesting. So the output is 0. So false. So if we have test 1, which is all trues and then a false, and we use comparator 1, A less than B, and then we dereference where this is pointing, this is going to find the first, it's going to point to the first element that's greater than or equal to true, which is, which index though, right? Really I want the index actually, let's do it that way. P1 minus the 0th index, standard out 0. That's interesting. That's also why this when we advanced it. So this was the first. So if this is less than or equal to, then I think we end up all the way at the end, right? We actually end up at end, which is 5. And it should be, there's 0, 1, 2, 3, 4. So the 5th index is all the way at the end. So that's kind of interesting. That's kind of what I wanted to show or expose, is that this comparator A less than B, it's going to be false for true against true, right? It'll just immediately be false. And this assumes that when this is false, that's the greater than or equal to, right? Like this is sort of, by the greater than or equal to assumes that this is a less than comparison. So actually what you would want is to get the first time you have a false, sort of going backwards from true and false, you actually want a greater than comparator. You actually want this comparator. And now you're going to get this spot here. 0, 1, 2, 3. You're going to get index 3, I think, here. as the returned value. No, you get 0 still. Shucks. It's greater than or equal to, maybe? Yeah, okay. Interesting. Pretty interesting. The way the lower bound works, I think lower bound is greater than or equal to the first value that's greater than or equal to, whereas the upper bound is the first value that's strictly greater than. So actually we want the upper bound then in this case. And then we don't have to put the equals in there. Yeah, we'll still get what we're after. And then we also want to show index 2. So it's a little confusing to do it this way, I think. If we do P1 minus so index 0, 1, 2. And actually the index is it's 0 index, but the number of nodes themselves is so you actually wouldn't have to decrement by 1, but that'll give you the index of the node. So what we're going to do, we're going to want to look to do is actually use this in this custom comparator. We're not going to use booleans, we're going to use integers, and those integers are then we're going to call the subroutine to get the Boolean value if it's true or false, and then do a comparison and do a reverse comparison. We're going to use the upper bound to find strictly greater than, and it's going to be A greater than B because it's true down to false, right? And Booleans, you can true is greater than false, right? They compare them in integer comparisons. So that's one way to do this. It's pretty nifty approach. I wish I had done this what we're practicing right now before I had walked into the interview, because then I could program this in the interview. You know, like I have a much better grasp now of being able to use these custom comparators and using upper bound, lower bound to manipulate, to like basically quickly implement a binary search without having to like finagle with the details of figuring out how should I code it. Because you really don't have to code it. I mean, you can do it this way. This is a very standard stock way of doing it, and it takes a little bit of practice. But this is kind of a really valuable, important skill, because not valuable or important, but like, yeah, valuable and important because it probably comes up day to day. You know, you have to do, you might want to do binary searches here and there, and then also. In interview questions, like it's a very common thing to be asked to at somewhere in your algorithm to implement a binary search, and it's super efficient if you can just throw in a custom comparator with a simple routine that'll give you, you know, sort of one part of the search that you're looking for, and excuse me, and also then you can you can even throw in an extra routine to convert these values to something else, right? And I'm wondering now, actually, if there's a way to do a pre-processing step. So this algorithm will be a logarithm squared, meaning the height log of n squared, the height of the tree squared, O of the height of the tree squared. And there's something, I'm gonna give this a thumbs up too, because I really like this question. I had it in an actual interview, and it's pretty nice to come back to this and revisit it. There's something else here that's important that I want to say, which is I'm wondering if there's a pre-processing step that you can do to. No, I think it's I think it's efficient. Yeah, because if you do any kind of pre-processing step to avoid the routine to determine from an index to a Boolean value, right? Whether or not the node is there, true or false value, then if you do that pre-processing step, you'll have to do that probably for every node at the bottom of the tree, and every node at the bottom of the tree could be basically n over 2, right? Half the tree could be at the bottom. And right, because what we just showed before, where the geometric series, it's a complete tree total. I mean, not a complete tree, a completely filled tree would be 2 raised to the h plus 1 quantity, total quantity minus 1, and that means that if you add another height, right, you basically multiply by 2, roughly multiply by 2, and so effectively half of the tree, O of n over 2, is at the bottom of the tree, which is pretty interesting. Kind of an unusual, like not unusual, but like kind of interesting property about binary trees. Yeah, you basically have O of n time if you try to process the entire bottom, potentially O of n time if you try to pre-process the entire bottom set of nodes. So actually you don't want to do that. So what we're going to do is try to solve this then, because it's actually pretty should be relatively straightforward to do this. What we're going to want to do is, I think, get the depth. So, or really we want, we're going to have a subroutine, which is, no, yeah, you need the depth first. Yeah. So get the depth. Initial depth. We're going to do a int height equals 0. Do a while. We're going to say really a for loop of a tree node. T equals root. We're going to say while t equals t. We're going to go to the left, right, and going to say increment. It's actually even simpler than that. Plus h. And then we're gonna print the height. I just want to make sure I got the right height before I say this is absolutely the way to do it. I'm gonna get rid of all this too. I can come back to this later. Yeah, C++ is great, man. I really like it. It's awesome. Okay, so for this tree, the height is 1, 2, 0, 1, 2. So I want to print 0. T is the root. Oh, while t. So 1, 2, 0, 1, 2. It should actually yeah, I'm thinking you decrement h one more time because t is the root. Interesting. So yeah, this is calling h1. Yeah, this is kind of a tricky thing, but the problem with this routine is this is calling h1 1. So because what's going to happen is h is 0. There's a node there. Increment h by 1. So we actually want to start this off at -1, right? And then so I want that to be 0. So this should return 2. Right? And then we say, okay. So the height is 2, or yeah, I mean, we can do it this way too. This is fine. Let's just say starting from 1 to, start of the first height is 1. We'll call the first height 1. That's fine too. Well, that's okay. Not a big deal. We'll just understand that as it is. So get the height. And then what we want to do is write a subroutine that uses that height to find whether or not there is a node at a particular, it uses the height given a particular index. We want to know whether or not the node at that index at the bottom of the tree is there or not, right? Kind of interesting subroutine, but so determine if bottom level node at index I exists. So that's the subroutine. So let's say bottom level exists, and this subroutine is sort of this subroutine is pretty important and kind of tricky. So we have the height, and we're given some int index, and we have first we have a sanity check that the if index is greater than or equal to 0 and index, so it has to be less than the total size at the bottom, right? And it says already it can be between 1 and 2 raised to the h nodes, or 2 raised to the h minus 1. So it's got to be less than 2 raised to the h, which is 1. We can bit shift to the left h, I believe. Let's say if, just say if not, then return. Really, it really should throw here. But we could just return false also. That's fine too, I think. And so if the height is 1, you have at most one node. If the height is 2, you'll have 2 nodes, right? Two the first. Oh no. Yeah, h minus 1 we need, I think. Yeah, that right. So if the height of the tree is 3, you'll have 2 to the first nodes at the top, 2 to the 0 nodes at the top, 2 to the first node, 2 nodes at the second level, and 2 to the height minus 1 at the third level. Yeah, okay, that's the way to do that. And so the index would be 0, 1, 2, and 3. Right. Pretty interesting. So now how do we move through the tree? How do we move through the tree to get to the correct index, right? We have to go sort of left and right. Well, to move through the tree to get to the right, basically the right leaf, is we want to use a while loop if we can, and we want to say the left side of the tree is going to be 2, depending on the height that we're currently at. It's basically going to be half the nodes is to the left, the other half the nodes is to the right, half of whatever is left over. I want to say we have like a not current index. Let me think about this for a second. How do I? So this was something I kind of struggled with during the interview, and I want to say you could actually interpret the index itself as a binary sequence, and move left or right depending on that sequence. So, or at least if you go from the most significant bit to the least significant bit, I want to say that works. I could be wrong about that, but if so meaning, yeah, it's kind of funky. Like, this is kind of interesting, but yeah, I think you could use some bit manipulation here in the index to figure out their left and right maneuvers. And actually, the way to do it is just divide the index by 2. So divide the index by 2 and get the remainder. If the remainder is, which is to say, is that right? Is that the way to do it? If it's, I don't know, man. That's a tricky thing. No, it's the other way around. It's the most significant bit is the one that you're gonna decide first. If the index, if that's a 1, then you got to go to the right. If it's a 0, you got to go to the left. So you kind of want to reverse the bits and then, then process them. Or start at the most significant bit first, which is, How did I do this? I don't think I did this correctly in the interview. I don't think I did this correctly in the interview. Gosh. It's actually the height bit. It's from H, so we'll say D. We'll call the depth. We'll start off at D equals H, and what you're gonna do. Oh gosh. You actually are gonna go from the index at the bottom up to the root node. Is the way we're gonna do this. It's a really interesting way to do this, but so it's gonna be a for loop. We're gonna have a oh gosh, is that right? This is so funky. I think I have to do some kind of reversal here somewhere around along the lines. I think what I ultimately did was I just processed the bits and put them into a stack to reverse it, and then I popped the stack and then made the maneuver space off of that. I think that was the easiest way to do it, because it's kind of funky doing it any other way. So we'll just do it this way. It's fine. We'll just use a stack. So push in index bits to a stack. And we're gonna just say while, so int t equals index, and we're gonna say while it's non-zero t. I definitely didn't do this right, you know. I definitely didn't do this right. You actually need, yeah, and you do need the depth. Yeah, you have to go, each bit is another level, so you have to go int d equals h minus d. Gosh, this would have been really nice if I had done this. If I had done this, oh, no kidding. No kidding. No kidding. And make this a Boolean. And then we say t bit shift to the left 1, or bit shift to the right 1. Yeah. Oh gosh, man. Yeah, if I had done this previously, I don't know how I did this during the interview. I don't know how I even managed. I don't think I did. That's the thing. It's like I think I got really tripped up, because it's pretty like involved. You know, there's a lot of pieces here. I was proud of myself for getting the answer to the question, like understanding how to solve it, but coding it up, obviously I got tripped up, and you can see me coding it up here as I'm getting pretty tripped up. Kind of would have to do it like a few times, I guess, to like really be able to kind of do it on the spot. Wait, where is this going off to? What is the... Shouldn't this be here? Anyway, so Okay, we're gonna push the index bits into a stack, and then we're gonna use this. We're gonna use that stack, and the number of bits we're gonna use, it's exactly going to be the depth of the tree. Now, we said we're gonna put the height as, so the height is 3, right? 3, 2, 1. Yeah, this will be, as long as this is positive, right? Then this will execute. Yeah. So once it hits 0, it won't execute, right? I think this is correct. So then we can say use the bits from the index reversed to trace path down to the correct index at the bottom of the tree. And return whether a node is present or not. All right, now we just do a simple for loop, tree node, I'll call it t equals root, and while t, we're going to say and also int d, or end we're going to say bits and not bits dot empty. And what we're going to do is we're going to say, this could be a while loop too. Could make this a while loop. That's probably better. Check is going to be bits.back. We're going to say bits.pop back. And then we're going to say if check. If it's true, that means we're going to go to the left. Otherwise, we're going to go to the right. Right, so no, if it's true, we go to the right. If it's not true, we go to the left. The right side means larger values, the left side means smaller values, right? And so now, and then now we say all the way at the bottom, turn t equals null pointer, or not equal to null pointer. If it's null, that means we return false, or that means we don't have a node there. And if it's not a null pointer, then we don't have a node there. So pretty kind of involved subroutine, right? That's the thing. This is like kind of one of the more important parts of the algorithm. And then finally we can run our routine, which says basically you have standard array of, or not array, but standard vector of integers from, oh no, you can't do it that way, can you? Because, oh gosh. Oh, that's interesting. No, you can't create it. You can't use this. You can't use this lower bound because this operates over a. This will operate over a container, and the problem you run into here is the container is So actually, you need to run this. You actually need to copy this. Oh, that's interesting. So, and modify this. Oh gosh, so I was wrong. Actually, it's a good thing I'm running through this again, because this is a challenging question, man. This is a tough one because it's just the calculations and whatnot. The problem that you run into is iterating over a container. You don't actually want to generate a container that has all of those indices to iterate over. I didn't even think about that, because like I said, if you do that, it's O of n time. You waste a lot of time and memory time creating that array, right? That's not optimal. So actually, you do want to copy, and then we'll do a binary search using this comparator. We're gonna effectively copy paste this. So we want the upper bound, not the lower bound, which is slightly different than this one, and we want to use greater than. So this comparator is going to employ this subroutine. This bottom level exists, and we're going to use. It's actually you'll see it does. You reverse these values and then use a negation. So this is not less than, and then we want greater than, right? Or not less than, or not actually not less than, but not greater than or equal. So if this is A is less than B, if you do B less than A and then negate it, right? That gives you, what you're after. So actually we just use this subroutine here, a modified version of this. And the thing that's kind of tripping me up here is why, hold on. Why aren't these braces matching up? These braces should be matching. I don't know why that's happening. Where is this matching to? Okay, these are here. These are fine. Oh, I think, so this should match, these should match. Where does that match? All the way down there? I think I'm missing some braces. Missing a couple. So this one, just throw in a bunch of braces. So where does this one match? There. So there's an opening brace somewhere here that we just don't know where the match is. What is going on? How did that happen? What? What do you mean? What is this then? I don't know. I don't know what's going on. This doesn't make a lot of sense. I think I might need to just refresh the page. I think something happened with the, and then this should be, why is it matching there? This should be matching with this guy. Yeah, this should be unnecessary. What is going on? I don't know. I'm gonna just copy this. How the heck do we mess up the braces? Oh, I have an extra one of these. That's what it is. Oh, this one. So this, and there we go. Okay, that's why I was wondering. was wondering how this could be. T of different type. Oh, index T. Could just do it call this X. This doesn't really need to. I'm just thinking like temporary value. Okay, so all right, compiles. All right, that was confused why it's not compiling. So we got to modify this binary search. And we don't need a forward iterator anymore. We just need so count is this distance from first to last. So we could say, and what did we say? First is, okay, first is some iterator and last is some iterator. Okay, so we would have like, I usually use begin and end, but you could do first and last too. So int first is going to be 0, last is going to be this 2 raised to the h minus 1. And actually it's inclusive, this range, so we subtract 1, right? And then you say, okay, that's first and last. So count is going to be this distance, so last minus first index plus 1. And I have this forward iterator it, so it int equals it equals, or just it, we'll call it. Could set that to be first initially. It's got to be set to first initially anyway. Or x, we'll call it x, I prefer x instead of it. So x equals first, and you'll say count is greater than 0, well count is greater than 0, x equals first. Step is count divided by 2. Advance step, so x plus equals the step. And then obviously I could technically make this like an iterator over basically like a generator where it's an iterator over, excuse me, integers that don't exist. If that makes sense. I think it's simple enough to just kind of modify this though, modify this search over a range. This is kind of like, you could do it this way too. And then comparator, so we're going to use this comparator, custom comparator comp. It's going to look like the following. It's going to say you're going to use, it just needs bottom level exists, I think. That's all you need. Level exists. And you have const int a, const int b, and you're going to say bottom level exists, return bottom level exists of a, bottom level exists of b, and you want greater than for this. We're going to use the negation of this comparator. We're going to use comp, and we're going to use the, so it is now x, the value at x. It's actually just x. Right, the point, you would use the pointer, but we're not going to use the pointer. We don't need to use the pointer. The sort of the index represents itself, sort of a thing. Oh, excuse me. Oh no, wait. Wait a second. Oh no, wait a minute. Uh-oh. Oh gosh. I did this wrong, didn't I? I did. Um. Oh no, this doesn't even make sense, does it? No. No. Oh gosh. There's no way that I programmed this correctly the first time around. It's like impossible that I did it. I got so confused now. No. The values. You have this custom comparator comparing against this value. Part of the problem is the value itself should be the same type as the element in the container that you're looking through. So the issue though is we're not. It's yeah. So we're kind of what do you call that? Modifying a bunch of things here, which make it a little bit awkward. It still can be done, however, basically you're given an integer. So this function is given an integer. It's so confusing. That's so confusing. You can kind of hack this a little bit by making the value, giving it 0 as the value to be greater than, or less than rather, the first value that's greater than, to the right, because 0 is always going to return true in this function, because we know it's always there, right? Yeah, by definition, it's always there. So it's always true. So this will still work if we just use 0 for the value, which is kind of funny. However, I don't think that's not exactly what I would like to do. What I would like to do is give it the value that this is I know this is going to translate to, and not have to call that routine repeatedly, and somehow say, okay, during this comparison, yeah, well, I guess we'll just, yeah, all right, fine. It's pretty funny. Yeah, that's interesting. So, well, all right. Okay. And last one is first plus 1 is the count. First step, increment by the step. Now the comparison you want to do, all right, so we want greater than, not greater than or equal to. So if you do, so this is like a less than, this comparison. So it's A less than B. Not A less than B is A greater than or equal to B. So what you want to do is reverse these and say value and X. This is value less than X if you do the negation of value less than X. So B, yeah, value A less than B. Before, I think also there wasn't a comparator there. There wasn't a negation. Yeah. So if you reverse them and negate it, that's when you're going to get. If you have A less than B, and you want greater than, if you do the negation of A less than B, you'll get A greater than or equal to B. If you do B less than A and then do the negation, you'll get b greater than or equal to a, or a less than or equal to b. I'm so confused. I managed to confuse myself. Oh gosh. Comparing the iterator to the value. So this will give you greater than or equal to, or not less than. The first value that's not less than. This will give you the first value that's not less than. If you do x value. The first value that's not less than. So you want the first value that is greater than. So you reverse these two. How would you remember that? I don't know. How would you remember that? I don't know. I don't know. And x is the iterator, right? And now count minus equals step plus 1. Otherwise, think about the step, return first. And this will give you the index. So this is sort of a subroutine, I guess. Bin search now of, you don't need to return. You know. No kidding. This is so confusing. This is so confusing. And then you're going to say return, it's going to be this depth, which is h minus 1, really minus 2, plus which. Something like this. Oh man. And step is also an integer. G. And it works. Of course it works. This is like, come on, man. This is ridiculous. This is too funny. I don't know, man. This is like, you can't do it. I can't do it. Wrong answers, though. Okay. Interesting. All right. Let's look at one. Oh boy, I feel like I have to come back to this one again. So let's do wow. Okay. There's no way I did this right when I was during the interview. It's not possible. It's way too much. Okay, so this is complete. So this one we should end up with the height is 3. Your height minus 2, which is 1. 2 raised to the first gives you. Oh no, that's why. Should be a minus 1 in there. Actually, yeah, the witch actually has a plus 1 too. So this is somewhat. There's a minus 1 here for this term, and then a plus 1 for the index. Oh no, the index has plus 1 already. No, wait. Because the index, if we get index 0, then excuse me, that counts as a node. So you actually do have that plus 1. Okay, there's a bunch of pluses and minuses going on here. But yeah, so you should get 3 plus 4. The index should be 3 here, and then you should get +2, and then, no, you should get 4. What does this do? This height. It's good. This is good. It's too funny. Okay. All right. The height is 1, 2, 3. You want 2 squared minus 1, which is -1, right? Let's print what these are. Let's actually just print these. That makes things even more complicated too, just getting all the... I see why they asked this question, man. This is a freaking, talk about a challenging question. Oh man, this is so like, what a pain in the neck. Okay, so that's 4. So there's a subtract 1 to give you 3, right? Those are the internal nodes. And then you gotta add 1 to which to give you the index. Now, what's interesting about which is it's gonna give you, so 0, 1, 2, 3 is the third index. It's actually gonna give you the value following. So you don't need to add 1, but you do need to okay, so that may be what I did wrong. Yeah, there's a lot of like adding and subtracting different parts, which is kind of funny. That might be why I got these things wrong. No kidding. Oh boy. No, still wrong. Okay. Let's see what's wrong in these different cases. So now the first case to 6 is wrong. Okay. What happened? So this should give you 3 nodes, and then this index should be 0, 1, 2. It'll give you the third index. So the 3 plus 3 gives you 6. So why don't we get 6? Why do we get 7? We got 7, and let's print these. First piece and the second piece here. Okay. So I got the first piece right. The second piece I got wrong though. The second piece I got 4. So the index shouldn't be 4. Somehow I got 4. Alright. What? No! After all that work, all that effort. Excuse me. All that modifying, copy pasted code. First, last, inclusive, right? H minus 1 is 4 or 3, yeah, so 0 to 3. And we said, okay, count last minus first plus 1, which is 4, so count is 4, well, count is positive. X is 0, step equals 2. 2 plus equals the step. If not, compare the value in X, which the value we said is 0, so this is true, and X is index 2 is also true, right? Visualizer 0, 1, 2 should be true. 6. Then, right? Hopefully this bottom level exists is working correctly. Can actually print the comparisons at each point, I think. So we'll value. We can say index. Let's do it this way. Index is, we'll do this. Say index is is x, and we'll say value is bottom level exists of x, and then we'll say comparison. So what this is going to do is, if this comparison is true, then we're going to set the first to be x plus 1. That means we're gonna move to the right side. If the comparison is true, we're going to move to the right side, which in this case means that if the first value is greater than the second value. Yeah, so if you have true and false, we're going to move to the right side. Actually, it's the way, and this comparison, we want to say, right, now, if it's true and true, we still want to go to the right. That's the thing. It's true and true, we still want to go to the right. So, because we're trying to find the first time that it's greater than, not greater than or equal to. So if A is less than or equal to B, or rather if the spot you're currently looking at is less than or equal to, so if the value is less than or equal to x, or no, excuse me, x is less, if x is less than or equal to the value, you want this to return true. This section. X is less than or equal to the value in terms of the comparison. X is less than or equal to the value. That means that compare x and value is true. You want to go in here. However, that comparison is just a less than or equal to, is just a less than comparison. So we want to do less than or equal to, so we flip these two values and negate it to get a less than or equal to. Right. So if we have a less than or equal to, then we want to move to the right, which means we're going to get the smallest value that's strictly greater. And then the comparison, we also are going to flip the comparison to a greater than instead of a less than, because all of these values are flipped in the array. So I think this is correct so far. I think the problem might be that this bottom level exists doesn't give us the correct I think this bottom level exists just doesn't give us the correct return values, I think. And so this will give us the next index over. Now, this doesn't give us, I think we need to do this. This might be part of the problem. I'm actually not sure now. This could and or should go off the right side, the right edge. That's something I'm not sure about. Does this go all the way off? This should go to the end. In other words, it should go one past the last part in the case where you don't find this should be a 3. This which. That's the thing I'm kind of uncertain about here. Why is that not a 3? 0, 1, 2 should be just right here, 3. Okay, well, what do we get for this? Index 2, value 0. Right, so that's false in index 2. Okay, that's a problem. Yeah, that's not correct. Right. 0, 1, 2 should be true. Okay, why did this? All right, so this is just wrong. This routine is wrong. That's the problem. That's gotta be it. Why though? Is it this? There's no way I would code this right first time around. First time seeing this. I think I have to look at the discussion. No. Why did we get 0 there? Why though? Why? Why would you get 0 there? So there should be like a right, left, right kind of deal going on. So index of 2. All right, there's only one bit to look at at an index of 2, or one bit that's sort of relevant, I guess. Oh, yeah, well, that should be fine. Right, left. The height is 3, so we're saying right, left. 0, 1, 2. Right, left. Yeah. That's exactly what you should do for 2. Right, left. Index 2, value left. Wait, what? Huh? Wait, what? What? Oh, left, right, left. Oh, why is there a left, right, left going on? Oh. Wait a second. Left, right, left. Uh-huh. That's a little confusing. Whoops. Oh, now we're right. Okay. Okay. That's a really, really subtle mistake. Has a lot to do with kind of going back and forth between the height and the has a lot to do with going back and forth with the height and the depth and having different things going on. Oh gosh. Okay, it looks like we're correct. Yeah. This is interesting, you know. This is interesting, to say the least. Oh gosh, man. This freaking question, man. Gee, this is the question I got in my interview. This is such a hard question to code up the first time you see it. This is such a challenging question. All right, I think we got it. We'll give it a shot. I'm assuming that, you know, this is not an input, the one that has runtime error. Oh, no kidding. By the way, also you need to sanitize the, like, even checking that it's a complete binary tree in the first place, by the way, is you have to verify that. Verifying that takes linear time, at least, as an aside. It looks like that's not an invalid test case. That's interesting. All right, let's give it a shot. Hey, we got there. Oh gosh. Okay. This took me a very long time to solve. Gosh. Gosh, no kidding. No kidding. No kidding. Excuse me. Wow. Excuse me. Excuse me. Yeah, so I had the right idea initially. However, coding it, yikes. It's challenging. But this is kind of a general approach you can use. One downside to this, so this could be a little bit faster if this value of this comparison that we were using, if we didn't need to run the routine repeatedly. And basically I would say something like, if you could just default, like I know the 0 is always going to return true. Excuse me, the 0 index. However, the way this is set up, it kind of has a kind of a specific approach. But yeah, you can always implement this kind of on the spot, as it is for any kind of binary search you need to do. If you're iterating over a container, you can use the lower bound, upper bound. And if you're iterating over a range, you also, these are iterators themselves, right? So it doesn't necessarily need to be a container. Like you could actually have iterators over, I want to say iterators over like the integers, something like that. Let me see if that exists, like C++, iterator over integers, something like that. I don't know if that exists. we don't want to iterate over an array. We want in Rust, like I want without creating the array. That's kind of what I want to do, is iterate over just integers. You could create like custom iterators, I guess, a custom iterator that represents like a range of integers. I wonder if you could do that. Kind of would like to try that. Obviously, it seems like it's a little bit easier to just modify this this lower bound, upper bound routine, which basically says, okay, you have a first element, a last element, first iterator, last iterator. X is initially the first iterator, or set that to the initial iterator. The value is another. Is an actual value, what the iterator sort of resolves to, if you were to dereference it. And then there's a step, which is also an integer. And then you have the count, which is an integer, which is going to be the distance between the first and last iterators. And then while the count's non-zero, start your iterator off at the beginning, wherever first is, which is the first part of the range. Make the step be the count divided by 2, so it's the size of your range that you're looking at. Increment x by the step, and you say, depending on a comparison, you're either going to move to the right or move to the left, or not move to the right. So moving to the right would mean you reset your first iterator to x plus 1, right, which is just sort of the next value after the beginning of the range, right? Or rather, yeah, this step range, it's going to be just after it. You update your beginning of the range, and then you update your count to, you're going to decrement it by how much you just stepped forward plus 1, right? Because you just you decrement it by the amount you just stepped forward, and you have to remember you also stepped with an extra 1 here. So that's how you update the count. Now the new range is going to be that size. Otherwise, you now what's interesting here is that you don't need to ever touch last again. Otherwise, what you're going to do is you've already moved x. Yeah. So x starts at the first iterator anyway, right? So it'll just update to the beginning again. But now the step, if you didn't move, now the step, the count changes to the size of the array that you're now considering. So this is a pretty interesting way to do it. But basically, the way it's done is that you're going to maintain the size of the array and some initial point that you're interested in. So you don't have to ever care about where the last point is, or the last part of the range, because the count plus the first position gives you the range that you're considering. So that's how this operates. It's a pretty simple routine. I like this a lot. And then obviously you could use this lower bound or upper bound with so like basically memorizing this is really useful for any binary searches you might need to do or might want to do. And you just have to kind of recall like this comparator, how that works, what that does. Really, if it's true, you're going to move to the right. If it's not true, you're going to go to the left, and then you can modify. You would consider the comparator to be a less than. So if you do a not a negation and you swap them, then now it's doing a less than or equal to. And then you would sort of code up your comparator accordingly. Now in this case, we're able to sort of quote unquote iterate over integers by just swapping iterators with integers. However, you could have a custom iterator that does iterate over integers, which would be interesting too. The only thing I don't dislike about this, that's kind of funky about this, is this comparator takes integers, right? And so the value itself, even though in the comparison we do a conversion from the index that we're considering to a Boolean value, inside here, I'm trying to think of a way where we can kind of keep the general form here, but still be able to pass true or false, yet still do this this conversion routine, which you could modify things so that this does a conversion first and doesn't do the conversion on the X. So like you could actually do the value, we'll say, you could do this if you wanted to. You could say bool value equals, in this case, I think it's true we want. Yeah, the first value that's greater than true, or the first value that's first value that's greater than true, and because this is reversed, it's going to be the first value that's less than true. And then you can say, instead of comparing, now the comparison you can do. You can actually modify this to have a second comparison. Could do it this way, which is really just a typical. In fact, you could even go so far as to inline this if you wanted to. And then X is going to be bottom level exists. Right, if you did this, still correct, I think. For some reason not as fast. Not obvious as to why. And then in fact you can even inline the comparator and say and just do not, if the comparison is A greater than B, right? A greater than B. Which becomes why is it taking more time now that I make these changes? Value less than or equal to. So yeah, you could really, if you really wanted to, you can go, you can kind of modify. You could really modify the binary search such that you're not even using these extra functions anymore. That's interesting. It seems to have slowed down. Somehow using these functions, it's faster. I don't understand that at all. I don't get that. That's kind of interesting. And being less than or equal to is a value being less than or equal to true, 1 being less than or equal to, so 1 will never be less than false. So then you could even get rid of this. So say that, right? It's ultimately what that comes down to. Oh man, it's taking so much time. Look at that. It was so fast initially, and now it's slowed down after these changes. You would think that it would be better after making these changes. Okay, I think it's kind of random, but that's kind of fun. Wow, whoa, wowee, okay. Yeah. Huh. Huh. Um, and at some point the count is 0, then you stop. Pretty interesting way to do this. Why would this be faster if we? No, I think it's just random. How fast it executes. Anyway, pretty interesting. Pretty interesting. Yeah. So the two key, really key portion. There's like a bunch of pieces to this, but the two key pieces are one, like recognizing what the first thing is recognizing what the algorithm is, right? Basically, find the depth. You can get a certain amount of the nodes just from the depth. You already know how many nodes there are, sort of internal nodes, and then you just have to count the leaf nodes, and then you can use a binary search to figure out how many leaf nodes there are, and you just have to add the number of leaf nodes to the number of internal nodes. That's the algorithm in English. In code, though, however, it's a bit involved because how do you implement the binary search is tricky. So I created two pieces. One routine, it's given some index in the leaf. Sort of if you were to consider the leaves as like an array, there'd be an index for each leaf. So given that index, you want to traverse the tree down to that index and determine whether or not that leaf exists there. So you can write a subroutine to do that. That'll return true or false given that index. That's what this bottom level exists subroutine does. And then the other subroutine, the other routine that you need is actually a binary search over given those indices until you find the correct index. That is the first element to the right that's that doesn't exist, that the leaf for which a leaf doesn't exist. Yeah, the first index to the right for which the leaf doesn't exist. Unfortunately, this subroutine, how it's written, this routine, how it's written, will actually go over the edge, so to speak, with the iterators or with the range, that's initial range. It will actually go over it if there's none exists. And setting this up properly is kind of tricky too, because it's sort of a backwards search where it's sort of like an array of at each index is true or false, and the left side is all true, and then at some point there's a false, and you're trying to find that index where it's false, and then you would actually subtract 1. Now, because the index is 0 index, you would, if it was 1 indexed, you would subtract 1 from that index to figure out how many nodes there are left to right, including up and to and including that index, or not. You would subtract 1 because that node. Yeah. So if it was 1 indexed, you would subtract 1 from to get the number of leaves, because you're 1 node to the right of the last node. However, because it's 0 indexed, that index actually is also this number of leaf nodes, which is also a confusing part of this. It's just like a kind of a subtle point, but it's like you would subtract 1 to get the index of the last node leaf node, and then you'd add 1 to count the number of leaf nodes given that index, given that 0 indexed position. So you actually don't have to add or subtract 1. That value you get is exactly the number of leaf nodes. And then the number of internal nodes is going to be the depth, and now you have an issue again with the depth where it's you could have it 0 indexed or 1 indexed for the height. And I opted to go with 1 indexed for the height, which kind of was possibly a mistake, because I ran into some issues considering when I was running my doing my calculations. 1 indexed seemed to be actually a poor choice, because you ended up subtracting a 1 all over the place, and it made things really confusing, I think. Let's do this 0 indexed and just modify everything accordingly. pretty sure that really threw me off too, trying to make that one index. It's kind of always better to do zero indexed things, I think, in my expert opinion. Oh, okay. Exponent is negative. Oh yeah. Don't need that anymore. I think this has an extra parentheses now. Yeah. So yeah, zero indexed I think is better. And then also, yeah, then also have to decrement by 1. This is part of just geometric series formula. So then you say, okay, well, how do I traverse the tree downward? Given this index, how do I traverse the tree to get to the node that we're looking for, to check if it's there or not? Well, what you can do is actually take the most significant bits left to right of the integer, the index, and that'll tell you which side of the tree you should be on, the left or the right tree, right? If you think about it for a moment, you realize, oh, if there's 32 nodes on the left side and 32 nodes on the right side, and there's a bit for 32, right? Either the index is 30 greater than or equal to 32 or less than 32. That's that 30. That's the bit for the 32. That's and then sort of the significance would be the not 32. I'm sorry. Yeah, 32. Yeah, 2 to the 4th, 2 to the 5th. So that would be the 5th bit. Would tell you whether or not it's greater than or less than. So that tells you actually which part of the tree to go on, left or right. So the issue I had with that, though, is that I had to actually get the bits into a stack then in order to reverse them, because I wanted to consider the most significant bit from left to right. I could have actually done this in a different way as well. I could have actually, instead of using this, pushing them into a stack, now that I'm looking at it again, I could have done, you actually would do this. You'd have int, not x, you'd have int d equals h, and then you would say check is going to look like this. It's going to be 1 bit shifted to the left d times, and then you AND that with the index, or with x, right? And then you're going to actually decrement d, right? So the depth bit, that's the most significant bit, and then you have that set to 1, and then you AND that with your index, with the number, and that'll tell you if it's just true or false. So you actually don't need the stack portion either at that point, I believe. Wrong. Oh no. Uh-oh. This could be h minus 1. No. I got that. I was wrong about that. I thought you could. I think you could do that. Push back is the least significant bit. Should be the last one that you look at. No, and then you don't need bits empty anymore, because that's just going to always be empty. So T, and you really don't even need that, and really D, I think. So when D is 0, and D greater than or equal to 0, I guess. I think that's what you need. Let's see how that goes. No, it still doesn't work. I don't know. Shoot, what did I do wrong? You need to have a terminating point though. Yeah, what is it? It's yeah, you no longer need to go the number of bits that you would push back here would be exactly how many bits? If the height is like 3, then you'd push back 3 to 1. If it's in 0 index height, 3 to 1. 3, yeah, 3. So the thing that's interesting is that you're always going to have the head. You don't need there's one bit you don't need to jump left or right on the head. So it's actually height minus 1 is how many bits to consider, I suppose. Excuse me. Yeah, pushing the bits back into a stack keeps it really simple to think about. However, you can do this with just using a instead of using a stack, like selecting the correct bit to address first. So I think I guess if you had like, I don't know, if the number was 5, and what's would be the depth? So if the depth is, let's see, 0, 1, 2, and the index is also 2, so you'd have, 1, 0. Since the depth is 2, you've got to do a right and a left to get there, right? So the first bit is a 1, the most significant bit is a 1, and then the next bit is a 0. So that's why you do 1 is right and then 0 is left, and you're at the position you want to be at. Now, in order to get that 1, you would need, it's actually d minus 1 here, which is kind of interesting. I think let's do h minus 1. So you have 1 is already at the first position, and then you bit shift to the left 1, and then decrement D, and then you don't have to bit shift anywhere, right? D is 0, so it's just 1, not bit shifted anywhere, and that's a 0 with X, and then you're done. I think that's the only issue here, is that you don't need to consider you consider h minus 1 bits. That's the way to think about it. H minus 1 bits. Yeah. I want to say that's what you've got to do. Runtime error. It's negative. Exponent is negative. Is it though? Wouldn't this be? No, still wrong though. Really? Why? How does that work? How? What? I'm really confused. By the way, I'm super uncertain as to why it's not working. And I would get this wrong, I think, in the future as well. I kind of have to debug this to figure out where I'm wrong with my logic here. So then Okay. What do we have here? Height index 0, height index 0. Okay. Well, what? X equals index, no? Oh, that might have something to do with it. Might have something to do with why I'm so confused. Left, right, left. Yeah, it should be one less than the height. Okay, now it's correct. All right. Yeah, and then this doesn't. This could. Ooh. This does need to be greater than or equal to 0. Yeah, because it can go on 0. It. You know what you can do? You can actually do d minus minus here. Nah, that's fine. Let's keep it simple. Oh, okay, now we're correct. All right. I was wondering. All right, yeah. The index needed to be. Need to use the index, right? Because x actually gets destroyed here. That's probably has something to do with it. I didn't realize that. But yeah, this is the right idea. Okay. Kind of funky though, like to think about it this way. Like kind of tricky, and you actually don't even the check you can get rid of, right? You could just throw this right in there. In this check. You know. And this is a much better. This is a much more efficient way to do this, because then you don't need to even think about these other pieces. Or much more like, yeah, I guess terse way to do this, to think about it. I like this approach a lot better. A much better way to express the idea. Okay, let's get rid of pushing the bits in there. Let's say, what else? You can make this a for loop now. No, it shouldn't be a for loop. A while loop is fine. Yeah, it's fine. Technically, the for loop, you could put the minus minus d in there. Yeah, you could if you wanted to. I mean, it's not really that big of a deal. Actually, no, that's not a good idea. Don't do that. Never mind, because these are different. These two values that you're initializing. But anyway, pretty neat though. Pretty nifty that you can do something like this to traverse the tree. I like this a lot. I don't think I did something like this. I think I tried to do something like this during the interview, but I think I did it wrong. So you have this, you get the depth, you got the subroutine to get to the bottom of the tree, given some index, which you can do a little bit of bit manipulation to figure that out. You just have to go, the most significant bit is either left or the right of the tree, and then you return the whether or not it's null, and then you also can write a binary search employing that subroutine. Then I would opt for a binary search routine that uses a first spot and the length of the range, right? So you cut the length of the range down. That's the step, and you can keep modifying the count appropriately to figure out how many elements are sort of left in the range that you're operating on. Excuse me, and then you're done when obviously the range is empty, right? Yeah, and then your if else it's going to update, in both cases updates the range, and just either decides to move the front of your range up to basically halfway through, or not, right? And the step is just going to be half the range. So either update. So you set x to be initial point. Now the reason they use X in here is it's supposed to work with iterators, so you can advance your iterator by this amount. Obviously, we're not using iterators, so we don't have to advance it. But that's a sort of a temporary iterator that points to the front, then advances it halfway with the step, and then advances it. If that point is if we should look to the right of that point, or then you're going to advance it one more time, and then update the count to remove the amount that you've advanced. And that's what all of this is going on. You would advance X and then set first to X. This actually, you can do this with iterator syntax, as this works too. Plus plus X just means advance by 1. Yeah, and the comparator you want to use, you can figure that out for yourself. Obviously, if you write this whole binary search instead of using their sort of version of it, the STL's version, then you can modify the Boolean condition of whether or not you should go left or right. And this is going to give you the first thing to the right that's isn't, I guess, the first thing to the right that isn't, for which this is, I think, not true, something like that. Yeah, so everything to the left of the index you get, this will hold true, and everything to the right, including that point, this will be false. That's kind of the way to understand what happens to this if condition. Yeah, so okay, pretty neat. Yeah, more concise way to write this is as shown. There we go. Yeah, it's kind of random how fast it is, but 86% of solutions, I'll take it. I'll take it. Yeah, get the height, zero indexed height. This routine just depends on the height. You just one bit you don't have to consider. There's just one bit you don't need to consider, and then and that's it, man. That's it. All right, we spent kind of a lot of time in this. Let me get going. I will. I'm not sure what I'm doing. Next, I'm gonna give my friend a call because he's called me a few times, and then see what's going on with him. I'm not sure if I'll be streaming later today. I might do other problems, possibly. But this is a great problem. This, like I said, I actually had this question during a FANG interview, and it's a tough question to code, like code on the spot. It's not too challenging to kind of figure it out, but it's definitely challenging to code it because there's just a lot of these little pieces and a lot of like sort of off by one type errors that you can make that you really got to be careful. It's a very good question, I think, to ask a candidate, because if they're really on top of it, that's a pretty good signal if they get this one right, that they're like pretty well prepared. The idea is not too hard to understand, but the actual implementation is definitely pretty challenging to get it right, in my opinion. So again, thank you again for watching. Talk to you all soon. Don't forget to hit the subscribe button if you like the video, if you like it, and subscribe. Yeah, I'm not sure if I'm going to. I might stream later today. We'll see. I might want to spend time with my friend too. So one or the other. We'll see. So yeah, take care.